Okay, so today's topic is PAULI paramagnetic susceptibility. Okay, so when magnetic field is not applying, that means B is equals to 0. So this is the case of without magnetic field. You can say without magnetic field. Without magnetic field, each of the free electrons, that means that maybe whether its spin is up or down, will have the same energy and also same density, right? So when there is no magnetic field, the free electrons, whether it's spin up or down, will have the same energy and same density of states. That is denoted by Ge. Okay, so for up spin, Ge equals to same density of states, that means G up spin, G down spin is equals to half Ge. Okay, so this is the case when we are not applying the magnetic field. Now when we are applying the magnetic field, that means with the applied magnetic field, so the density becomes, so for up spin it will be half G E minus mu B. Similarly, so this density of states for electron spin parallel to field. Okay, similarly for down spin it will be half G E plus mu B. So in this case, density for electron spin anti-parallel to field. Okay, so here are some graphs are there. Same density of states. Okay, in this axis, that is total energy. Total energy is kinetic plus magnetic of electrons. Okay, this is parallel to field and this is opposite to field, and the distance between these two is 2 mu b. The distance between this is 2 mu b. So, and here another diagram is there. Okay, see density of, you can also write this as density of orbitals, right? Density of orbitals. Okay, density of orbitals. This is parallel to field, up spin, down spin. Okay, so see from the graph that we will have more number of up spin electrons, free electrons, than down spin free electron when we are applying the magnetic field. So this excess amount is shown in this second figure. Okay, so and will contribute to net non-zero magnetization of the system. So it will contribute non-zero magnetization of the system. Okay, so see now if N up and N down, So this is the number of electrons with spins up, and this is the number of electrons with spin down. Then we can write n up will be integration DEFE G up spin E G. Okay, this is density of states when up spin is there. Fe, this is the Fermi Dirac distribution function, which gives the probability of occupancy of any energy level. Okay, any energy level. Similarly, n down spin will be integration DEFE G down by G down E. Okay, so this is the representation of n up spin, and this is for n down spin, and here Fe is the Fermi Dirac distribution function that gives probability of occupancy of any energy level. Okay, so now in the limit when mu b divided by kbt is very less than 1. See, mu b by kbt is very less than 1. So we can expand these two terms, that is G up spin E and G down spin E. So then the expression of n up spin E, n up spin will be, so n up spin will be how much? Now it will be 1 by 2 integration DEFE. Now we expand this term, it will be GE minus mu BB del GE by del E, right? Similarly, for down spin it will be 1 by 2 DEFE GE plus mu BB del GE divided by E. Okay, simply we expand this to density of states, that is for up spin and down spin, in the limit mu b by kbt is very less than 1. So now using these two equations, so what is the value of magnetization M? So its formula will be minus mu b n up spin minus n down spin. Okay, so by putting this value from these two equations, we get up spin magnetization will be mu b square b integration DE FE del GE upon del E. So this is the expression of magnetization by using this formula and these two equations. Okay, so now integrating by parts, it will be, now we are integrating by parts. So see, mu b square b f of E GE in the limits minus integration DE del f of E del E G E C. So here we are integrating by parts. See, the first term inside this bracket will be how much? It will be 0. Why? Now because at, we can say, at lower limits G equals to 0, and at upper limits your Fe equals to 0. So this is the reason behind this. The first term will be 0. See, again the second term. See, this second term contains the derivative of Fermi Dirac distribution function. So which is equivalent to this thing. This is equivalent to a Dirac delta function, that is minus delta E minus EF. This thing is equivalent to Dirac delta function. So the above equation will be now M equals to mu b square b integration dE. See, this thing is 0 and this minus will be plus. So the expression will be now delta E minus EF GE. Okay, and we know, so EF will replace this A, replace this E, so it will be mu B square B G of EF. Okay, so this is the final expression of magnetization M. So this is the required expression for Pauli spin magnetization, that is due to free electrons. Okay, so see, it is independent of temperature. See, there is no temperature is here, so it is not of Curie's law type. Okay, so if we are considering density of states at Fermi level, that is EF, in 3 dimension, then see, the value of GEF will be how much? So GEF will be 8 pi root 2 divided by h cube m to the power 3 by 2 EF to the power 1 by 2, or also you can say 3n by 2 EF. Okay, so hence just put 3n by 2f instead of GEF, it will be, therefore m will be mu B square B into 3n by 2 EF. It will be 3n mu B square B divided by 2 EF. So this is the expression of magnetization. So now Xi will be susceptibility del M by del B. So it is also known as Xi Pauli. So that is equals to 3n mu B square divided by 2 EF. So this is the paramagnetic susceptibility. Okay, so see, while deriving this result, so it is assumed that the spatial motion of electron is not hampered by applied magnetic field. Okay, by applied magnetic field, the spatial motion of electron is not hampered, but the wave functions are modified by the field. Okay, so see, Landau, so he had shown that this contributes to diamagnetism with susceptibility. That means we can say Xi Landau is equals to minus 1 by 3 Xi Pauli. Okay, Xi Landau is equal to 1 by 3 into Xi Pauli. So the expression will be minus 1 by 3 into 3n mu B square divided by 2 EF. 3 got cancelled. We are left with mu B square divided by 2 EF. So this is the expression of Xi Landau. So hence now we are finding the net susceptibility. Okay, net susceptibility of the system due to free electrons. So Xi is equal to Xi Pauli plus Xi Landau. Okay, so it will be C, Xi Pauli, instead of Xi Landau I can simply put minus 1 by 3 Xi Pauli, minus 1 by 3 Xi Pauli, and it will be 2 by 3 Xi Pauli, and 2 by 3 Xi Pauli is 3n mu B square divided by 2 EF. 3 got cancelled, 2 got cancelled, we are left with n mu B square divided by EF. So this is the net magnetization of the system due to free electrons. Okay, and see, this EF, this is the Fermi energy. So the value of EF is h cut square divided by 2m 3 pi square n power 2 by 3. Also you can say EF is equal to kBTF. So TF is the temperature that is equivalent of Fermi energy EF. So, or you can say TF is Fermi temperature. Okay, this is Fermi temperature.